Heyo, and welcome back to the 6502 tutorial series on how to use the 6502 single board training computer. This is, I believe, episode 5, and we're going to expand on what we did last episode, which was getting a basic program to even run on here in the first place, in the form of a simple infinite loop, by learning how to do some I.O. We have relatively limited I.O. options on here, but I think it's just enough to be fun and dangerous, and you will see later on in the series you can actually do probably more than you even think that you can do on this thing. But for the moment, we have our output register here, which we've shown before, which you can write 8 bits to, and we've got these dip switches here, which are in programming mode when this is set to, when run is set to off. These are for, transferring data onto the bus into RAM, but if you are in run mode, this circuitry rejiggers itself so that these are actually also readable as an input device. If we bounce over really quick back to the project page, you'll remember we have this memory map here, where most everything is RAM, but you've got this kind of chunk in the middle of the memory space, which is, if you write to it, it writes to that register. If you read from it, it reads from these switches. And that's what we're going to expand our little loop with today by just doing an infinite loop that this time also, while it's infinitely looping, reads from these switches, writes it to this output, and it's just going to do that forever. Doesn't sound super exciting, but you'll actually finally be able to see your machine do something, so that's cool. Let's dive straight into it. So again, on the project page, there is the 6502 CPU instruction reference. There's a few places you can look this up, but this is the MassWork one that I like. And we're just going to need to, like we did last time, look up a few instructions. Now, I am not going to cover in depth again how you get this thing up and running, which takes a couple steps. If you need to remember that, or if you need to kind of practice it some, I'd go back to the previous episodes where I went over how to set up the reset vector and get this thing reset and running. But I'm pretty much going to gloss over that, and we're going to stick to the standard that I've been sticking to, which is always pointing my reset vector to 0200 hex and just going from there. So don't expect to relearn that from this episode. If you need to remember it, go back to the previous ones. But basically what we'll need is the same jump instruction that we were using last time, which is, you can see it's still even here, jump to new location, which we are still going to use, but that is going to be our last instruction, because the idea here is basically, right, that you need to read this. It's going to load it into the CPU, and then you take that value that you just loaded and you write it back out to here. And then, and only then, will we jump back to the beginning, that first instruction that will read from here, load into the CPU, then the next instruction will take that value from the CPU, move it out here, and then the jump. That'll jump back to the beginning. So, the first thing we need to look up is, what is the command for reading from anywhere? So, reminder that the 6502 is super cool because it's incredibly simple. And really all you have here is your 8-bit data bus, your 16-bit address bus, your clock signal, and your read-write signal. And that's more or less it. So to access these devices, you just access them as if you were memory. So you're learning the same thing here, whether you want to read or write a memory location or you want to read or write one of these I.O. devices, really only differs in where you're reading or writing to or from. And in this case, we know that there's anywhere in that region from 4000 to BFFF will read or write from here or here. If you do it anywhere else, pretty much it's going to be reading or writing from RAM. But it's going to be the same exact mechanism. So let's look that up. If I go back all the way up to the big old table, which I'd say is a relatively decent place to start looking. If you have never done assembly programming before, then this might be really cryptic. Throughout a lot of platforms, some of these instructions will look pretty similar. So if you look at this table, you can be like, oh, there's JSR or, push A. But presumably you haven't. So, you can also just Control F this page, and I am going to look for load. And the other nice thing is just below that table, and this is one of the reasons why I like the Masswork page, they have instructions by name, and they literally just give this nice list where it is the mnemonic, the 3-letter code that you would use if you were writing assembly, and then a description of the thing. So we've got load accumulator, load X, and load Y. So now I'm going to dive just a little bit deeper, and we will come back to this because the question is, the heck is the accumulator? What the heck is X? What the heck is Y? Because load makes sense, right? That's you're putting something in something, but like, what are those things? And we haven't gone over some of the details of the architecture yet, because every CPU is kind of a little bit different, but most of the concepts are the same. But when you're working at an assembly level, you kind of need to know exactly what the CPU looks like in general. So you can already see there's this thing called accumulator A in here. And what this is showing us is the microprocessor programming model. You will generally see something like this in a datasheet for any kind of CPU under a similar name and with a similar kind of diagram. And what this is showing you is all of the registers inside of the machine. And a register, you know, I keep using the word register for this thing, and that's more or less just what it means, is a single, I'm going to call it a word-wide location somewhere in the CPU, that, you know, it's not over here in the RAM chip, it is not external to the chip, it's inside the CPU, and it's kind of one of the fundamental building blocks that you can do operations on, because you can load stuff from memory, but ultimately, when you actually are doing work, you are mostly loading information from memory into a register in the CPU, and then doing something between registers, and then possibly writing stuff back out to RAM or another device. But the registers are the little super fast locations of memory, or, you know, pieces of memory, memory devices that actually exist on the CPU die that things get loaded into and that get stored, you know, that get stored back into RAM. But they are kind of the things that the instructions really operate on for the most part. And since those are kind of the most important part of the CPU, you'll always get this diagram that shows you what registers exist, how wide they are, and you'll know I use the word word. The word word, boy, that's going to become a tongue twister, is generally used in programming parlance to describe the native data object size for a machine. So it's really hard to like say that in a really, you know, come up with a really uniform way of saying something like that. But the point is, put in plainer English, this is an 8-bit machine because its data bus can transfer 8 bits at a time, right? It's 8 wires. So the native word size on this machine is 8 bits. It's an 8-bit machine. So like if you had a Motorola 68K processor, one of the early ones that's really got a 16-bit bus, the word on that machine is 16 bits. And it gets a bit confusing with like x86 processors because they also call a word 16 bits on there because those processors were 16 bits for quite a while, and that kind of became their legacy. Like they were briefly 8-bit, but then quickly went to 16-bit, and then a lot of that baggage stuck with it. So generally what they call the word on an x86 is 16 bits, even though that doesn't make any sense because like the native data size on almost all x86 processors at this point, because they're all 64-bit processors, is 64 bits. Anyway, that's what a word is when I use the term word. So registers are generally a word wide, again, because that's kind of the native size of things that the machine deals with. And what you've got here, you can see there is, like I said, the accumulator A, the index register Y, index register X, the program counter called PC, which we've alluded to before, which is, see, this is showing you how wide it is. So these ones were 8 bits wide, but the program counter is 16 bits wide, which makes sense because the program counter puts out the current address of the command to execute on the address bus, so it kind of needs to be 16 bits wide. There's also a thing called the stack pointer, which shows a 9th bit over here that's always set to 1, we'll explore that a bit more later on down the road. And then you also have this processor status word, which is a register where each of the bits means something specific. Most of this we'll be ignoring, but the point is, what this thing is telling you is that all of the assembly instructions or machine code instructions that this thing executes do some kind of operation involving one of these things. Like the program counter generally can't be accessed like a normal register. It's mainly affected by, jump instructions that will change what's in here. But the accumulator on the 6502 is kind of the main register. It's the register that, by default, almost all of the math operations operate on. And then you've got Y and X, which are similar, but they don't. Most instructions, there are really no instructions that have these as the default target for math. So you can do adds with the A register and subtractions and things like that. But you generally can't really do that with these, because these are used more for memory access and indexing operations. I realize this is a lot to throw at you. The important thing to note is that I had to show this to you at some point, and the fact is there's a bit of memory in the processor that goes by the name A, and most instructions operate on it. And you will generally be loading something into A, or the accumulator, or doing some operation on A, or taking the contents of A and putting it back into memory. So now that we back up a step, the main thing to take away from that is that there is this command called LDA, or load A, which loads the accumulator. And we want to load something into the accumulator. So let's just go with that. And if we click on this, this will take us to the definition of how this is used, what it's called, all of that good stuff, like with the jump instruction we were looking at last time around. And you can see there are a bunch of different ones. Remembering, if you don't remember from last time, that at least the way that this document is set up, it kind of has all of the related instructions under one section, and then all the kind of the versions of them listed out. And you can see, of course, they are all actually different instructions, because the opcode is totally different. You've got A9, A5, B5, they're all different. The thing they have in common is that they all take something from memory and load it into the accumulator, but it depends on how they do that. So we can get into more complex ways of doing that. These are called addressing modes later on. Just know that there are a bunch of ways to address memory. So with the jump, you can kind of describe the jump that we did last time as using immediate addressing, even though that doesn't, talking about addressing at all with a jump command is kind of a little wiggy. But regardless, because it had the opcode and then immediately the 2 bytes for the address in memory directly after it, it kind of becomes part of the instruction, and that's called immediate data, or it's an immediate addressing mode because it loads the data immediately after the instruction. We're going to use an immediate mode here as well. Or actually, that's not true. I'm actually a liar. We are not going to use immediate mode. We are going to use absolute addressing, which is one of the modes in here. So I'll gloss through these really quickly. You'll see the first one is immediate, and this does exactly what it says. It'll have your opcode, and then immediately after it in memory will be the literal byte that you want to load into memory. So if you wanted to load, the value 01 into the accumulator, you would use load A 01, or you'd write A9 and then 01, and that would literally read A9, say, oh, the CPU would say, oh, I need to read the next byte and put that into the accumulator, and then it would read the next byte and zoop it into the accumulator. But we are not going to use that one today. We are going to use absolute addressing. So absolute addressing, instead of grabbing just whatever the next thing is in memory, it actually does grab the next thing in memory, but it doesn't use that as the value to put into the CPU. What absolute addressing for load A does is it reads the instruction, in this case the opcode AD, which is what we're going to put in here, and then it expects the next 2 bytes almost exactly like that jump instruction from last time. It expects the next 2 bytes to be the address in memory from which to load the value. So again, this gets into, you have to think indirectly, much like the reset vector, where it always looks in a memory location for it to read what the actual memory location to start from is. It's indirect. Absolute addressing, also indirect. So, for example, if you wanted to read whatever's in memory at 4000, which, would be our switch, or usually I use 8000 for no good reason, you would want load A from address 8000. And the way that would end up looking is that you'd have your opcode, AD, and then your address, again, in that kind of reversey little endian order, where the small part comes first and then the big part comes second. So if you wanted to load from 400, what you'd have in memory is AD, your opcode, then, or from 200, or from 400. I'm going crazy. No, 4000, that's what it was. I'll remember this. I'm doing this a little bit late at night, this one. Anyway, so if you wanted to load from 4000 hex, it would be AD, followed by 00, the low part of the address, 4000, and then the next byte would be 40, the high part of 4000. And what the CPU would do would be read that AD, say, okay, I need to get the address that you want me to read data from, and it would get the 00, put it in the small part, take the 40, put it in the high part, and then read from 4000 whatever's there, right? A little bit brain melty if you haven't done any of this stuff before. It's tough for me to. One of the toughest things about teaching this stuff is that once it clicks with you, it kind of becomes old hat, and then it's hard to teach it because you don't remember what was hard about it in the first place. This is not to flaunt. It's just that this is a real thing. You'll find that it clicks at some point, and then you don't remember why it was difficult. So it will happen for you too. But that's how we load stuff out of memory, or something, in this case it's going to be the switches that show up as a memory device into the CPU. Now, if you can load into the CPU, then obviously there must be a reverse process, right? Where you can take something that's in the A register on here and put it back into memory or back out into some kind of output device. And there sure is. So if I search for store, there, we don't even have to go to that list. It's right here. We have kind of the matching instruction that goes the other way around. STA, store accumulator in memory. And I won't gab on about this one too much because it's easy to describe in that it does the opposite of what load A does. So you can see it has basically all of the same addressing modes. And again, we're going to use absolute for our purposes here. And it works the exact same way. You'll have 8D, which is the store instruction. The store absolute instruction, to be clear, because there's a lot of versions of store. And then that is followed by the address at which you would like to store the contents of A. So in this case, because we want to store it into the output register, we are going to store A 4000, which is the address that this thing is mapped into, and that's going to go the same way. So it's going to be 8D, then 00, then 40. So the opcode, then the low part of the address, then the high part of the address. It's going to read that, it's going to read the address, then it's going to actually read from that address, or sorry, this is story, so it's going to write to that address whatever was in the A register. This will make more sense when we slow it down, start single-stepping through this. But what I'm going to do is, since we're getting a little bit more complex here, firstly, that's all the instructions we're going to need. That's the whole thing, right? We are going to load A from the switches, then store A into the output register, and then jump. That's the whole thing. But since it's starting to get a little bit involved, I'm going to start writing things down, which I didn't really plan for, so bear with for a moment here as I cross my fingers and hope that I have a good pen sitting around. Yeah, this'll do. Good enough. Actually, do I have anything more marker-like? I had a really nice dark pen around here, and of course, the second that I'm streaming, I don't see it. So I'm just gonna have to stick with plain old pen, and we're just gonna have to suffer through. So what I'm going to write down here are those instructions that I need. So again, I'm going to, let's just switch back straight to this, because I don't need that screen for a moment. And I'm just gonna write down what that program was gonna be, right? So it was just gonna be load A from, I'm going to stick with 8,000 because that's just the address that I use. 4,000, 8,000, they're the same anywhere in there. And then it's going to be store A, 8,000. And again, remember, it's a little funky here because it's the same address, but it's two different things. Because when you read, it reads from here. When you write, it writes to there. It's the way it's wired up, but they share the same address. And then we're just going to jump. And what I'm starting to write here is assembly. You generally write assembly because it's an easier way than just writing down the machine code to remember what's going on, because it's pretty relatively easy here to say, okay, right, I'm loading into A from address 8,000, then storing from A to address 8,000, then we're going to jump. And generally, when you're writing this to, this would be at, if we did this thing the way I'm going to, this would be at address 200 hex, right? Because that's where I'm going to load everything in. That's my arbitrary choice of where I'm going to start putting in my code into memory and where I'm going to start executing from. So this would be at address 200, and I would put jump 200, right? It'd just be jump to address 200. Or we can put the dollar signs in there too. I hope that this is as difficult to read for you as possible. But anyway, we don't have to do that. I'll scratch out this whole version, because when you're writing assembly, and this is not really useful for us now, it kind of is useful when you hand assemble, and it's really useful for when you're actually using an assembler. But instead of having to know and remember actually exactly where we're at in memory, you can get a little bit more abstract and use a label. I just had a stink bug fly into my face. Hey, bud. That was a thing. Anyway, so I'm just going to call this, I don't know, main. It's arbitrary. And that's going to be my label for where we start. And this is just for bookkeeping purposes, right? And then it's going to be the same thing. Load A from 8,000. Store A to 8,000. And jump. And this is where that label becomes semi-useful. Jump to main. And now it's relatively easy to read. We can just see that this is going to be a loop where it's going to load A from 8,000, store A back to 8,000, and then it's going to jump back to main. And we don't really care what the address of main was. Makes it easier to understand. Then I'm going to do exactly the reverse of this to start hand assembling this, which is going to be taking what I've written down, the program that I came up with here, and turning it into machine code so I have a nice little listing that I can put into here, just, you know, something to reference. So this is my kind of semi-human readable assembler version of my program, and I'm going to start converting it into hexadecimal stuff that I can actually flip into these switches. So we know that I'm going to load into memory at address 0200. That's just my personal choice, so I'm going to write this address here, and at 0200 I'm going to put in the load A command. Now this is where we need to start going back and referencing this document again. So let's go back to load A. And this gets easier the more you do it, because of course you kind of memorize what the commands are. Okay, so here was that information for load A. So load A absolute was AD. So I am going to write that down. AD. And I'm going to write out each byte explicitly. You know, if you're doing this, you might write the same byte on more than one line, or you know, more than one byte on one line. But I'm going to write it out really explicitly here. So at 0201, that's going to be the low part of our 8000, right? So that's going to be the 00, 00, and then 0202 is going to be the high part of the address, 80. So I'm just going to make a little note or comment here. This is our load A 8000. Now I'm going to do the same thing with the store A. So let's go back and look at store A. There we go. Store accumulator in memory. We're going to use the absolute version again, and that is 8D. So at 0203, I'm going to put the byte 8D. At 0204, again, this is absolute, so it gets encoded the same way as we did for load A. So first it's the low part of 8000, 00. 0205 is going to be the high part of 8000, 80. And then I'm going to make the same kind of little comment here to say that these lines are our store A 8000. And now we're down to our final command, which is going to be that jump. So let us review again what the jump instruction was. Jump absolute. Okay. I'm going to go back to the top of the page because clearly I've gotten to the bottom and there's a bunch of stuff down there that I don't care about. So let's. Here, I'm just going to click this link. There we go. Jump to a new location. We're using the absolute one, same thing that we did last time. So that's going to be an opcode of 4C. So at 0206, it's going to be 4C, the jump command. And then this uses that same little endian byte order to specify where exactly specifically in memory you want to jump to. Of course, we know, since we started at 0200, we're going to jump back to 0200. So at 0207, that's going to be the small part of 0200, 00. And then at 0208, that's going to be the high part of 0200, which is 02. And again, nice little note. This is jump to 200. Or main, because main resolves to 200. They're the same thing. All right, so now we have taken our program, we have written it down in assembly so that we could kind of read what we're doing, and we've taken that and we have boiled it down to the actual machine code instructions that make it up. So now the only thing left to do is to put it in memory and run it. Let's do it. Bear with. This is the extra exciting part. So first thing that I need to do, again, as always, is I'm going to set up my reset vector, and I'm going to set it up to 200. And again, as mentioned, that is an arbitrary choice. So at FFFC, I'm going to put in 00, 0. At FFFD, I'm going to put in 02. And that's my reset vector setup. So now I need to start putting in code at memory address 200. So that's where I start writing in stuff from my list. Again, we just got goobly-gook in RAM right now. That is to be expected. So let's work through this, and I'm going to kind of cross things off as I go. So at 0200, I need to put in AD. So that is, you'll get used to these patterns as you do this, but it's, an A is this, it's 8, 9, A, because it's 1, 2, 4, 8. And then D is 8, 9A, B, C, D. So there's our AD, and I'm going to mark that I did that one. And we will increment our address to 0201. 0201. I'm not going to do that every time here, but just try and keep an eye on how we're counting in binary, because doing this right will also help get your brain into binary world. So anyway, now we're at 0201, and that needs to be a 0. Super easy. 0. Done. Then an 80, but I gotta make sure I increment to the next address first, which is 0202. So that's gonna be 20202. And that is going to be an 80. So turn the highmost bit on. That is an 80. Done. Now we advance to 0203. 8D. So we already have an 8. And then we want 8, 9, A, B, C, D. O204. 0204. Now 0204, that's a 0. Done. 0205 is another 80. 80. Mark it off. 0206, 0206 has to be 4C. So that is a 4, 8, 9, A, B, C. So there's our 4C. Mark it off. Advance to 0207. That's 00. Store it. Mark it. And at 0208, we have an 02. So let's advance to 0208. 0208. That's an 02. And again, just kind of re-mention from the last one, the computer doesn't know that the program ends here. It just doesn't. The computer is super duper freaking dumb. The only reason this doesn't just kind of keep going off and executing things is because this last thing we do is a jump back to the top, and it's always going to do that. But when you're writing your own programs, always remember, if you do some instructions and then just don't put in anything afterwards, the CPU is just going to treat whatever comes next as another instruction, which is probably garbage, and it's probably not going to do what you expect. So either always do some kind of halt loop or put your whole program in some infinite loop, because otherwise it's going to do an unknown thing. But we've got a nice well-defined thing here where it's always going to loop back up to main. It's always going to load A from 8000, store A to 8000, jump back to main, and do that till the end of days. So let's reset this thing and see if that actually is what it's going to do. So as always, set your reset switch on. I have to hold mine down. Yours is a toggle. Yours is going to be, on, off. The position where it looks like it's more pressed down is the on position for you. But for me, I got to hold it down. And then I am going to switch this into manual mode, and I'm going to try and step this as cleanly as I can for you guys when I do this. But remember, my and your step button is going to be pretty bouncy because my debounce. I keep saying bouncy as if you guys know what that means. That means this might trigger multiple clocks per step just because it's basically a spring in here is what a switch is. So it literally bounces and makes contact a couple times if you are not careful. One of these circuits is supposed to handle that and clean that up, but it doesn't do it very well. So anyway, to reset the CPU, you hold down the reset and then you step it a few times, at least 3. And oh, it's not in run mode. That's also kind of a thing that needs to be done. Hold down reset, put it in run mode, then step it at least 3 times. I just do it a bunch. Out of paranoia. And then you can take it out of reset, in your case by clicking that reset button again, and we are ready to start watching the thing execute. So the first couple cycles are going to be garbage. You'll see these addresses are just random addresses. And then you'll be looking out for this one. This is our FFFC. And that is where it's beginning to read our reset vector, which in this case is the first low port of it is 0. And yeah, see, bouncy. You saw for a second it went to the next address and it read 0200, and you can tell it read the address properly, the 02 byte for the high part of it, because at this point we're at that address. We're at 0200, and you can see that first command here, which is that first byte, which is our command AD or load A, which is AD. So that still looks right. Let's see how cleanly I can step this thing, because the next thing it should do is read this 00 and this 80. So there's our 00, went to the next address, and there's our 80. And now if we step it one more time, now the address bus says 8000. There's our 80000. And you can see there's some data here. And the cool thing is, because we're single stepping here, you can actually see this in real time. These switches don't get like sampled when this address is read. They just get like put directly onto the bus. Like these just get connected directly to these wires. So that's the fun thing, is you can see as I turn these switches on, you can actually see what they are set to. Except these, right? Why are those on? Kind of ignore for now, but just know that when I said that these are, that reading from 8000 or whatever, that middle area in RAM reads from these switches, that's a little bit of a simplification. The top 3 switches are actually connected to some other stuff that we can play with in the future, but for now just remember that those are pretty much always going to be high. You don't get to use the top 3 switches because of the way I designed this. But you can set these to whatever. So let's just set it like that and go to the next instruction. And now you can see we're back into that 200 area because it's done doing that read and it's back to doing the next instruction. So now we're at 0203, which is that next instruction. We're at the store right now, and it's reading that story instruction, 8D. Right? And so it's going to do basically the same thing as the load A, where it reads the command, then it's going to read the 2 bytes of address, and then it's going to go to that address. So here we go. There's the 0, there's the 8, and now we're at 8000 again. And as you can see this time, it's not taking the value from those switches because it's a story. It's a different command. It had stored that value from the switches inside of the CPU in that A register, and now it is taking the value that is currently in that A register and it is putting it back out onto the bus to store into memory. So what this is doing right now, as you can actually see it already did it, is it is basically turning on this chip and saying, hey, please take this value and hold on to it. And that's how we have wrote the value of A into the output register. So that's our story instruction sorted. And now if we step again, we are now done doing that right. This remembers that value because that's what this register does. You write to it and then it hangs on to whatever was written to it last. And we're at our next instruction at 0206, which is the 4C, or jump instruction. And again, same basic pattern. Not all instructions have this pattern. This is basically what a absolutely addressed instruction looks like, and all we're dealing with so far are instructions that kind of match that pattern of command and then 2 bytes of address. They're not all like that. We'll get into some more different looking commands, but these are convenient because they all look the same, but not all instructions have this same form. Just want to be clear. So now it's going to read the jump instruction, reads the low part of the target address to jump to, reads the high part, which I clearly didn't write, and we can see our first bug because apparently I forgot to write that into memory, even though I checked it off. And you will watch clearly, as I will, that this is going to jump to this address, which is a good case in point because it's going to do exactly what you tell it to. Which, whatever this address is, I can tell because the way this is wired, it's if one of these top 2 LEDs is on but not the other, you are accessing the output or input device. And so you can see this is this is reading from the switch again right now, which is not what we wanted. So what I'm going to do now is I can go fix that. This is actually a really good example of being able to do that. Happy accident, didn't actually mean to do that. But if we go back into program mode, since this thing is still powered on and we haven't, messed with memory at all, we can just go right back into program mode, edit memory, and then restart the thing and run again. And because everything's still there, it'll just be fine. So let us, as you can see, these switches are still set to the last thing I had them at, which was that 02, 08, which is where the 02 is supposed to be, and it is not an 02, it's a bunch of crap. So let me fix that. There we go. Now it's an 02. So let's try this thing again. I'll speed through it a little bit because we've been going a little bit now. Usually these aren't this long, but let's go. Let's go. So same process. Our reset vector is still there in memory. We haven't changed anything, so we can just do our normal process of put the processor in reset, switch to run mode, step it a few times just to let it reset itself, let go of reset, and now we're cooking. So garbage, 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 garbage. Oh, see, so bouncy. We got all the way to our executing from 200 and didn't even notice it. So there's our 00, our 880. There's our reading of switches. Here, let's write a different value. Here's our next instruction, which presumably is the store A. There's our 00. There's our 80. Here is it, writing that value back to here, and you can see it took that value. And now here is our jump at 02, 06. There is our 00. There is our 02 as intended, and now it will jump back to that address, 0200. There we go, 0200. Fixed our bug. Beautiful. And as you watch, if I just keep stepping this thing, it's just going to keep doing that loop forever, right? And of course, like if I turn the switch off, it's going to take a minute because it's going slow, but it will update over there. There we go. Let's just turn a bunch of these on. And it'll keep doing that for forever. And so, of course, the fun thing is that we could just like fire this off into full speed mode. Let's just do it with the slow clock for now because it's just as good. Which, same thing, if you're ever going to change the clock, I advise doing a full reset on the thing because otherwise things can get screwy. So hold down reset. I'm going to switch the clock mode to slow. So you can see it's driven by this thing again, how fast that clock is. And I'm going to start it quite slow, and then you can see the loop speed up, and it will look pretty much like things are going directly from here to there because it's going so frickin' fast. So here we go. Now it's going to step through just like we were doing before. Garbage, 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 garbage. There's our load of our reset vector, and here we start execution. Same program, just running kind of on an autopilot clock now. And for the same reason, if I adjust these switches, they will eventually get red here. Written there. And so on and so forth. And then we can speed this all the way up. Well, not all the way. This goes up to 5 megahertz, and this is only a few kilohertz. But it's fast enough that now it looks pretty much instantaneous. How cool is that? It looks like we spent $50 making a board that connects switches to lights. But we can get fancier with this. But there we go. You're doing I/O. So if you got this far in the project and you managed to make it do this, check it out. You are making a computer do I/O. How cool is that? All right, I'm going to break it off real quick there because this has been like a 45-minute long video. But I hope you had fun, and I hope a lot of my rambling actually taught you something. All right, see you in the next one.